Oh, student stride here again. Today we're going to be going over notes for section 7.2, ionic bonds and ionic compounds. Got our objectives here. We're going to describe formation of ionic bonds and the structure of ionic compounds, generalize about the strength of ionic bonds based on physical properties, and categorize ionic bond formation as exothermic or endothermic. We'll review vocab, compound, chemical combination of two or more different elements. A few new terms we'll be getting as we go through the section. And our main idea. Oppositely charged ions attract each other, forming electrically neutral ionic compounds. That's our definition for ionic bond. Electrostatic force that holds oppositely charged particles together in an ionic compound is called an ionic bond. And compounds containing ionic bonds are called ionic compounds. Special type of ionic compound, binary ionic compound, just has two different elements, a metal cation and a nonmetallic anion. Here's a little illustration of formation of sodium chloride. Key idea in the formation of an ionic bond is the transfer of an electron. Illustrated here, you have a extra little electron out in this s orbital. It transfers over, fills up this p orbital, and we end up with a sodium ion and a chloride ion. During class time, I'll expand on this concept, talk more explicitly about what we need to do here. But you're going to have to be able to run through this particular process and understand how the ionic bond is formed. And this just shows you in a number of different ways. That the positive and negative ions exist in ratios determined by the number of electrons that are transferred from the metal atom to the nonmetal. And then this repeating pattern we call an ionic crystal. So illustrated here, you've got a whole bunch of chloride ions, a whole bunch of sodium ions. They just kind of stack on top of each other in a certain fashion. In this case, we get a little cubic crystal. In this crystal, we call a crystal lattice, three-dimensional geometric arrangement of particles, and it's what results in the structure of many minerals. And what causes this is a strong attraction between the positive and negative ions. Melting point, boiling point, and hardness depend on the strength of attraction. So something like that, all ionic compounds are going to have pretty high melting points, but some are much higher than others. And it's so like sodium iodide here, comparatively low melting point compared to the other substances here. Magnesium oxide, extremely high melting point. So it means the ionic bonds in the magnesium oxide are much stronger than in the sodium iodide. Got the same routine on boiling point. Magnesium oxide high, sodium iodide much lower. So because these ions are kind of locked into position, electrons cannot flow freely, they're very poor conductors of electricity. But if we melt them, make them in the liquid form, or put them in aqueous solution, dissolve them in water, Then we got charges that are free to move, so they conduct electricity easily. So in the solid form, poor conductors. In the liquid form, or in the aqueous form, good conductors. And when we talk about putting ionic substances in solution, in water, and we call that an electrolyte. Little illustration of why, if we apply a force to it, they break apart. They're fairly brittle. In an ionic crystal, we got alternating positive and negative charges. We apply a little force to that. We can get two positive ions next to each other, two negative ions, and we have a force of repulsion, and it breaks it apart. Couple of key terms: if we absorb energy, we're endothermic; release energy, exothermic. And the amount of energy required to separate 1 mole, later on we'll talk a lot about this concept of the mole. 1 mole of ions in an ionic compound is called our lattice energy. And lattice energy directly related to the size of the ions that are bonded. So we got smaller ions with closely spaced ionic charges. It's going to require a lot more energy. If you got bigger ions, it's going to require less energy. So electrostatic force, that's the force between the attraction of these things, attraction between inversely related, or it's inversely related to the distance between the opposite charges. Or, simple version, smaller the ion, the greater the attraction. And the value of the lattice energy also affected by the charge of the ion. So you can see when we get more higher charges here, like MgO, Mg is a 2 plus, O is a 2 minus. We have a large lattice energy, which is why earlier we had a very high melting and boiling points for the substances. And here to the Ki we talked about earlier, one of the smaller lattice energy, K has a 1 plus charge, I has a 1 minus charge, and K is a fairly small ion, and with just 1 plus, 1 minus charges and the size, we get a fairly small lattice energy, why they had a small, lower melting point, boiling point on that substance. A few quick review questions. Why are solid ionic compounds poor conductors of electricity? And it's that they do not have electrons or charged particles, if we want to be a little more general in nature, that cannot flow freely. Looking at some of the other ones, solids do not conduct electricity. That would not be true. Because metals, most metals are solids, they definitely conduct electricity. Electrolytes only if you put it into water, and here we're talking solid. And they're not non-metals because an ionic compound is made up of binary ionic compounds, metals and non-metals. And the electrostatic charge holding the two ions together, we just call an ionic bond. Next chapter, we'll look at what a covalent bond is. And these two really don't even matter. So that takes care of section 7.2. We will spend a little time looking at questions in class, maybe diving a little deeper into the things. But as always, you should be reading your book, concentrating, take good notes. Read the book, see anything else that looks important to you, add it in. So this is a great learning opportunity for you. So that's all for now.